Okay, so we're going to start computing some probabilities. So probability is an event that is always between the probability event is always going to be between 0 and 1. So remember that we talked about when we did things like relative frequency, those are actually technically kind of probabilities. And when we record probabilities, we record them usually as decimals. So when we have the 0, we know that means 0%, and this 1 is the decimal version of just saying 100%. The probability of any event sits somewhere between 0% and 100%. So any event, what we should expect to see is that the probability of it is going to be somewhere between 0 and 1. If an event cannot occur at all, so in that case, the probability of that event would be 0. That'd be like rolling a 7 on a 6-sided die. That cannot happen. If an event is certain to occur, then the probability of the event is going to be 1. So that'd be like if I toss a coin and said, what's the probability that it's going to land on heads or tails? Well, that's 100%. It's going to land on heads or it's going to land on tails. That covers every event that can happen. So technically, this here is what we call a theoretical probability, because it's not based on any kind of experiment. It's just based on what theoretically, using a bunch of math, we can kind of guess what's going to happen. So if a sample space has n equally likely outcomes, so that means each event is equally likely, like rolling a die. It has the same probability as landing on a 1 as it has landing on a 2, landing on a 3, a 4, or 5, or 6. All those events have equal likely outcomes. If we flip a fair-sided coin, it's equally likely to land heads, equally likely to land tails. This is when events to become not equally likely to occur, things get a little more interesting. But as long as, like I said, each event in the sample space, each outcome is equally likely to happen. And the event we're interested in has k outcomes, then the probability is going to be the number times the number of outcomes that fit in event A divided by divided by the number of outcomes in the sample space. My tongue's like too big or something. Anyways, or we would say k, because that's the number of outcomes, over n, which is the number of outcomes in the entire sample space. This is sometimes referred to as theoretical probability or a classical probability. Usually theoretical is more what you hear. We typically know this is a case where we know all possible outcomes and the probability of those outcomes, and we know they're all equally likely to happen. So this would be something like flipping a coin. We know when you flip a coin, it's going to land heads or land tails, and we know it's 50-50 on either. We know when I roll a die, it has a 1 out of 6 chance of landing on a 1, a 2, a 3, a 4, a 5, and a 6. And it's not going to land on any other number because we only have 6 sides on it. Same thing with poker hands. We know all the cards in a hand or all the cards in a 52 card deck. We know the probability of all those cards, so we can calculate the probability of poker hands without actually having to do any kind of experiment. Also, games of chance, so like lotteries. We know when we play the lottery, we know the probability because this is equally likely that you're going to get a number 1 on your ticket and they're going to get a number 1 than it is that you have a number, 32 on your ticket and they give you a number 32. So there's things that we know, all the things that can happen, and we know all their probabilities are the same. So as I mentioned, lotteries. As an example, in the Georgia Cash 4 lottery, a winning number between 0000 and 9999 is chosen at random, with all possible numbers being equally likely. What is the probability that all 4 digits are the same? Well, for one thing, between here and here, that is going to be 10,000 outcomes, because we have 9,999 we started at 1, but we're starting at 0, which adds on that one more number, puts us at 10,000. So those are my outcomes. For my event should have 10 outcomes because you're likely to get a 1, 1, or sorry, 0, 0, 0, 0, 0, 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3, 4, 4, 4, 4, 5, 5, 5, 5, 6, 6, 6, 6, 7, 7, 7, 7, 8, 8, 8, 8. These are all the things we can look for. And 9, 9, 9, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the probability of all 4 digits being the same would be 10 out of 10,000. So the number of outcomes for my event over total number of outcomes. So you have a 0.001 chance, which if you want to put it as a percentage, is a 1% or 0.1% chance that you would actually win this lottery. As another example, a penny, nickel, and a dime are tossed. We denote tossing a head as an H and a tail as a T. And we can note these three tosses. Let me try this again. We can denote these 3 tosses in order. So we're going to pretend like it's the penny first, then the nickel, then the dime. So your sample space is going to be this. I can get all heads. I can get a head on the penny and the dime, or sorry, the penny and the nickel, and a tail and a dime. The penny could be a head, the dime could be a tail, or sorry, nickel can be a tail, and the dime could be a head. Penny could be a head, nickel and dime could be a tail. And we can keep going through this, but this is my sample space. Like right here, penny's tail, dime is head. Sorry, I keep from forgetting the nickel's the middle. Penny is tail, nickel is head, and dime is tail. So it's just telling me all the possible ways this can occur. So I have 1, 2, 3, 4, 5, 6, 7, 8 outcomes that are likely. And they're all equally likely because they're all going to be fair coins. We want to know what's the probability that all 3 tosses are the same. So here we get all 3 come up heads, and here all 3 come up tails. So the probability that all 3 tosses are the same would be 2 out of 8. So all 3 tosses are the same. We just write P and we write that in there. So we know what event we're talking about. 2 of them are going to be all the same. We got all heads or all tails out of 8, which is actually 1 out of 4. So you could actually leave your probability as that, or we could say 0.25. And next, we want to know what's the probability that only 1 toss is going to be a tail. Well, here we only got 1 tail. Here we only got 1 tail. 2 tails, 1 tail, 2 tails, 2 tails, 3 tails. This one had 0 tails. So the probability of only 1 tail is actually just going to be 3 out of your 8. So that is 0.375. And then because this is a question we get asked quite a bit, is things like, what is the probability that more than 1 is going to happen, or at least 1? Let me get rid of that here. So we want to know, what is the probability of getting at least 1 tail? So you got to think, what does at least mean? Is at least the most I can have or the smallest I can have? So if I have at least one tail, this means that I'm looking at, I have one tail, because that's at least one tail. I can have two tails, because that's at least one tail. And I can have three tails, because that's at least one tail. So all of these events here have at least one tail. The only one that doesn't is this one. So this is going to be 7 out of 8, which would be 0.875. So you guys got to be careful with some of these because of the wording. Like I said, at least and more than. At least is another one we're going to bring back in a while, though. Okay, another thing that we commonly use for our probabilities is a deck of cards. So kind of go through just to the basics of a deck of cards so we know what's going on. A deck of playing cards has 52 cards in total. It's split into 4 suits, which is one is a heart, one's a diamond, one's a spade, and one's a club. So that means it's going to have, some cards are going to have a heart, some are going to have a diamond, a spade, um, a spade looks like a shovel, so it's the one that looks like this. And the club is supposed to be like the club you kind of hit people with, which might not be so obvious, but that's what this looks like here. It's supposed to be like a club that you smack people with. So these suits are your red suits. Diamonds and hearts are red suits, so we split it into 2 groups. And then usually our black suits are going to be the spade and the clubs. Each suit has 13 cards, and those 13 cards are going to be a king, queen, jack. And then we have 10, 9, 8, 7, 6, 5, 4, 3, 2. And with not one, we have an ace. We call it an ace, but the value is technically a 1. So we kind of interchange, basically treating it like a 1, but we only call it an ace. And then here we go, a picture of what a deck of cards looks like in case you're not familiar. We are asked here, and we're going to go back to that other slide to figure some of these out. What is the probability of drawing a queen? So remember, we know we have 52 cards in the deck. If we go back, how many of them are actually queens? Trying to grab my highlighter here. So we see we have 1, 2, 3, 4 queens. When we're asked how many queens we have, we would say we have 4 queens out of a total of 52 cards. If we simplify that, both those are divisible by 4, so that's actually 1 out of 13. And 1 out of 13 sorry, my calculator's just not being cooperative, is 0.0769, and it just keeps on going from there, but I'll round to the 9. A little over 7% chance that if you randomly drew a card out of that deck, that it would actually be a queen. The probability of a heart. Oops. So once again, if we look at this, we see that my hearts are right here. So a heart is a whole suit. So we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 cards in that suit. So in that case, the probability is going to be 13 out of 52, which is also just 1/4 of the deck because each suit takes up a fourth, which is 0.25. And then sometimes you're just asked about one card in particular. Here, let me move all that a little bit. 4 out of 52, 1 out of 13, 0.0769. And then we were asked about a heart. We said that is going to be 13 out of 52 cards, or 1/4. So next we asked, what's the probability that the card we grab is a red queen? Well, we only have two choices. This one and this one are my only cards that are queens with that are red suits. So we have 2 out of 52 cards. That's going to be 1 out of 26. Which is going to be approximately, this is an approximation too, but that's going to be approximately 0.038. And the last one was the probability of it just being a queen of hearts. Keep going back to the wrong place. So we see we only have one card that's a queen that is a heart. So we have one queen of hearts. That would be 1 out of 52, which doesn't reduce at all, which is going to be approximately 0.019. There's about a 2% chance that you pull any particular card out of a deck. If you want, and especially a queen of hearts, that's about 2% chance, almost 4% chance of a red queen, 25% chance that you pull out a heart, and we have almost an 8% chance that you pull just a queen. So here is going to be a little bit different. So there are 10,000 families in a certain town categorized as follows. Actually, I need to go back one slide. Sorry. So when we talk about things like populations, that is technically a probability experiment. So sampling an individual from the population is a probability experiment. The population is the sample space, and members of the population are equally likely outcomes. So each sample has its own probability of occurring. Every time I collect any kind of sample, it has its own probability that I would get that particular sample. One of the things to remember that when we are doing sampling, they are probability experiments. And because they're probabilities, we can't make anything certain. They're always subject to, the whims of the universe. So here is an example of that. So we had a sample of 10,000 families in a certain town categorized as follows. We have 4,751 of them own a house. I don't know what that 4 came from. That was an accident. Yeah, okay. Make sure I had that in the right place. Own a condo, we have 1,478. Rent a home, we have 912. And to rent an apartment, we have 2,857 rent an apartment. Okay, so every time I randomly sample a family, or each family anyways, they all have the equal likely chance of being selected. So we can kind of treat this as a experimental probability. Not experimental, I'm sorry, treats as a theoretical probability because every family has equally likelihood. So pollster samples a single family from this population. What's the probability that the sample family owns a home? Well, it's pretty easy. We have 4,753 people who families own a home out of 10,000. So that is going to be roughly, as we see down here, 47%. So 0.4753, so 47.53%. The probability that a sample family rents would be 2,857 out of my 10,000 people, which is 0.2857. So once again, oops, I think I did that wrong. Oh, that they just rent. I did not read my own problem. The probability that they rent, sorry about that, we have 912 people who rent a house, and then we have 2,857 who rent an apartment. And that's once again out of 10,000 people. So that is really 3,769 people actually rent out of my 10,000 families. Sorry, these are 3,769 families that rent out of 10,000 families. So 0.7369. So my probability is roughly about 38% that if I randomly picked a family, that they would be renting a house. And like I said, we can do this just like it is a theoretical probability because each family has the same likelihood of being selected as any other family. Just like when I'm rolling a die, each die roll has the equally likely chance of coming up. And the last thing to mention here before we go on to something a little different is unusual events. So when we were talking about standard deviations, one of the things that we were talking about was that if something was in two standard deviations of the mean, so this is your mean, two standard deviations away, mean, two standard deviations away, just the other side. But we said that what was in here was 95% of your data. That means cumulatively in the tails, we have 5% left over. It does not fit in this range here. So we have 50% left over. So 5% of data is over two standard deviations from the mean. So this is where this 5% comes from. So because 5% of my data is outside of that range in these tails here, it's outside of that range that is within one standard deviations of the mean. This is what we consider to be unusual events. So they're unusual because they're very unlikely to happen. So in other words, these events have a very small probability of occurring, which makes them unusual. There are no hard or fast rules as to just how small probability needs to be for an event to be considered unusual. And like some people think 5% is just too large to be considered unusual, and I might have to agree with that. And it's also dependent on other things involved with it because sometimes we're looking at individuals, but if you look at groups, then those probabilities look a little, carry a little more weight to them. So like I said, there's no hard and fast rules at how small probability needs to be considered unusual. The rule of thumb is usually 5% though. So that 5% comes from that fact that anything over two standard deviations from the mean has a 5% probability of occurring. So for an example, in a college of 50,000 students, we have 150 are math majors. A student is selected at random and turns out to be a math major. Is it unusual? Well, if we look at 150 out of 5,000, the probability that that occurring is going to be 3%. Because that probability that of finding a math major is 3%, finding one is unusual. So this is less than 5%. The probability or just finding a math major is unusual. You gotta be a little careful about throwing around something being unusual at 5%. Like I said, we're gonna get into this a little more deeply. If it's just like an individual, the probabilities don't mean as much. As we said before, probabilities tend to look at big systems. So finding one person who is a math major, I mean, it may be a rare event, it may be a little unusual, but like 3% isn't really that small when you can in consideration of what's going on. All right, so one more example of this. A company is conducting a survey of randomly selected individuals to determine the ages of a social media application. So far, they've collected 3,000 users of the application. So they mean app, phone app when they say application. So they found 3,000 users of the app have been surveyed. The frequency distribution shows the results. So we see that over here. So what is the probability that the next user surveyed is 25 to 34 years old? And is that unusual, unusual to grab somebody in that age group? Well, so that would be probability, somebody's between 25 and 34 years old, that we'd randomly, the next person who happened to come by and download this app, the chance they'd be in this range is 765 over that 3,000 in total that we have. So that probability is 0.225. So that is actually 22.5%. So this would not be unusual. We would pretty much expect that if this is something we expect to see is what it is. So if it's not unusual, it's expected. I have something on the bottom that won't move and it keeps cutting things off here. 6.5 out of 3,000. And we said that's 22.5%. So this is not unusual. Now, if the next person who came along happened to be 13 years old, who downloads this app, would that be unusual? So somebody who's up to that, not 13 necessarily, but 13 to 17, we have 84 people out of 3,000. In the past that came through and download this app were between the ages of 13 and 17. And the probability that this would happen is 0.023, or not 23, sorry, 28, or 2.8%. This is definitely less than 5%. So yes, this is unusual. So yes, the next user being between 13 to 17 years old is unusual. So just unusual, just more than anything means it's unexpected. It doesn't necessarily mean there's anything wrong or just like that. It's just, I don't expect to find a 13 or 17-year-old being using this app. I don't expect it. I expect it to find a 25 to 30-year-old using this app. So when the next user happens to be from 25 to 34 years old, I'm not going to be surprised by it. If the next person using that app happened to be between 13 and 17, yeah, that I might be surprised about. So it is less to do. It's not like, don't put a connotation on this concept of unusual. It doesn't mean there's anything bad or wrong going on. It's just we didn't expect it to happen. Like we don't expect to find somebody has an IQ of 155. There's a less than 5% chance that somebody's IQ is 155 or more. But those people exist. We just don't expect to see them.